GOD God, he's the God of sequences. Over here is the first keynote speaker. The last keynote speaker is Rutgers professor. You hear that?
Over here.
Oh yeah, okay. Taking attendance. And in the beginning, we had lots of very, very good speakers, too numerous to this. Before going on to Neon, let me just make another suggestion. Shareholders used to give money to solve problems. So I think even a better use of your money is to suggest donations in honor of the solver of the problem for the OEIS. That's what I do. So I hope that's all. Yeah.
So, thank you, Leroy, for suggesting this. Thank you, Gene, for organizing it. Thanks to all the other organizers. I never thought I'd see so many sequence stands in one place. So I'm going to talk about these things. I'll start off by talking about the OEIS and the future and so on. And the OEIS. So in 1964, when I was a grad student, I had a sequence I was trying to identify. I had a lot of sequences, and I started collecting sequences, and this is the cover of the notebook from about March 1964. And here's the page that has my first collection of sequences, and the sequence I was particularly interested in soon became A435, because it begins with, they were sorted alphabetically, lexicographically by the first term bigger than 1, and this it's filed under 8, so it's fairly well towards the end of the initial ordering. A1 was the number of groups who ordered N, and A2 is Collatz, and A435 is that one. I do this.
Neil, it's very hard for me at least to hear you.
Okay.
Good, that's easier.
Yes. A brief history from 1964 to 2010. In 1973, Academic Press published the Handbook of Integer Sequences with 2000, and then there was a long gap while letters and manuscripts came in and accumulated until there was, I figured, about a cubic meter of stuff. And Simon Plouffe offered to help, and so we wrote the encyclopedia in 1995 with 5,000 sequences. And then I waited a year until it had doubled. And people sent in sequences as soon as the book came out. So when it got to 10,000 sequences, I thought Academic Press could hardly object if I put it on the internet. And so that's when the OEIS was launched in 1996 with 10,000 sequences. And then it's sort of steadily grown at a fairly linear rate, at about 10,000 a year, 12,000, 15,000 a year right now. And so it was on my homepage at AT&T all that time. AT&T was very supportive. I owe them a great deal for supporting it for all those years, letting me play with it. But I began to worry about the future. So in 2009, with help from Harvey Dale and Nancy Everhard, we transferred the intellectual property to a foundation. We created a foundation called the OEIS Foundation and set up a board of trustees and transferred the intellectual property to the foundation, and we tried to move the database from my homepage to a space we rented from a public machine. And we ran into a lot of trouble doing that. And it took a whole year. It wasn't until Russ Cox stepped in and straightened things out and rewrote all the software that we finally got it running. That year, right, there was a lot of trouble. There was the mysterious person in the Ukraine that we tried to contact. The trouble was that the MediaWiki software was no good at handling sequences of numbers. And of course, that's what we needed it for most, the sequences of numbers. And it just didn't work. So it wasn't until November 11th, 2010, that we actually got it running. Russ got it running on the internet. It was launched. And at that point in time, there were 180,000 sequences. And since then, it's continued to grow. Sorry, okay. So today, the two magicians who keep it running, Russ Cox and David Applegate, my former colleague at the labs, who unfortunately couldn't make it here today. He's the systems administrator, but Russ is in charge of the underlying programs. And then we have the Board of Trustees. I'll just quickly read the names. David Applegate, Ray Chandler, Russ Cox, Susanna Kyler, Tom Duff, Ron Graham, Charles Greathouse, Richard Guy, Mark Lebrun, Robert Manafo, Simon Pluth, myself, and there were two former trustees, David Johnson and Tony Noe. And we have a board of advisors, Harvey Dale, David Johnson, Hilary Orman, who is the ombudsman for resolving disputes. I think we've only had one so far, but we have to call her in to help. Richard Stanley and Jerome Zalgeber. And we have a board of editors. We have 20 editors-in-chief, whose names are there. I will quickly read them out because I owe these people a great deal. Max Alexeyev, who is sitting there, and David Applegate, Jörg Arndt, who is sitting there, and Bruno Braccelli, who's in Bologna and couldn't make it, Ray Chandler from Texas, Russ Cox, Susanna Kyler, Harvey Dale, Neil Fernandez, Olivier Gerard, who is over there, who just arrived from Paris, Charles Greathouse, Richard Guy, who unfortunately wasn't able to come. He was originally planning to, but it's a long way from Calgary to come here. Paul Hanna. Is Paul here, by the way? I wasn't sure if he would be able to make it. Ron Hardin, who isn't here, another former colleague. Maximilian Hassler, who I know couldn't make it. Alois Heinz, who is here. Yes, finally got to meet you. Wesley Hurd, Robert Israel, Nathan Johnson, who is here. Yes, in the back. Václav Kotosovic, who I think is not here. Wolf-Dieter Lang from Germany, who is not here. Peter Lushny. Michel Marcoux from Paris, also couldn't make it. Richard Mata, Douglas McNeil, Robert Manafo. You arrived. Hi. Giovanni Restra from Italy, Michael Somos in the front row, Ralph Stefan, and Richard Zunkeller, who is, Reinhard Zunkeller, forgive me, who is here. Reinhard. We just arrived from Munich. And the major contributors, well, there are a lot, and too many to mention. So thank you to everybody, and in particular, there are the two people without whom it wouldn't exist. Harvey Dale, who is a very distinguished lawyer, very well known in other worlds, and we're very honored to have you here. Thank you. And Russ Cox, without whom it wouldn't work so fast. It probably wouldn't even exist if it wasn't for your your programs. So the situation today, we're approaching 250,000 sequences. We get about 40 new ones every day. There are nearly 4,000 registered users. I've collected about a list of 4,000 articles and books and websites that thank the OEIS. We get about 9 million hits a month, and we get a lot of traffic. So the future, I want to mention some problems. And one problem, the biggest problem that I see is should we hire a manager? Should we get somebody, because it's almost a full-time job running the OEIS these days, should we actually hire a manager to do this? And this would be very good for several points of view. The backlog of sequences waiting to be edited is now creeping up. It was over 300 yesterday. Of course, many of the editors are traveling to come here, so that explains that. So there are a lot of things. If we had a managing editor, it would improve many things. It would make everything would be more professional. It would make life easier for the contributors. There are a lot of things that need doing. On the other hand, it would require money. And we don't have much money. We operate on a shoestring. So either we would need a large endowment in order to pay the manager from the interest on the endowment, or we have to raise money every year, which would mean going out and begging for funds to raise it, to keep paying the manager. And either way, we need a fundraiser, and this is not something we could get. There's going to be a trustees meeting at 10 o'clock in room 433 on the 4th floor, and to discuss this more, perhaps. Another thing we could do is try to raise money for various projects. I've had this idea for a long time. We ought to have an exhibit about integer sequences in the science museums everywhere. And I suggested this in a couple of places, and you do a very good job of selling it, because nothing has happened about it. There are many other projects that we could ask for money to help with. We could try to make the OEIS. I've heard complaints that the OEIS is very hard to use if you're a student, a high school student, or a high school teacher. We could try to do more to attract people. We need more animations, movies, drawings, music, and we could. I was talking to Jörg Arndt about this. He was saying it would be really nice if we had a systematic way of presenting the formulas in the OEIS, maybe in the format used by the Centralblatt or something, so that they could be searched and systematized. We have to think about the long-term future, what's going to happen in 10 or 100 years. Another problem that we have is that web pages disappear, what's called link rot. We have thousands of links, and 1 in 5 doesn't work anymore. And that's because people's home pages disappear or they get moved around. So I had this idea back in 1996 that I hoped that some company would offer to set up home pages for people and guarantee to maintain them for a minimum of 500 years. You would pay a flat fee, and then if the format changed, that they would rework them. If it was no longer HTML, whatever replaced HTML, they would be updated and they would be preserved. And then if this were carried out, then we would have a much safer place. Web pages wouldn't disappear all the time. But nothing has come of this. Right? William?
Yeah, I tried.
You tried. Amazon Smiles, if you sign up for it, they pay 5% of your purchases to the OEIS Foundation. So unsolved problems. I thought that since Douglas Hofstadter is going to be here, and Colin Mallows, John Conway, and Jeff Ligarius, and Max Alexeyev, and a number of other people, we could settle this question. Does the Hofstadter Q sequence really exist? And unfortunately, Colin couldn't make it. Colin Mallows is not here. But, so this is the sequence. It's a bit like the Fibonacci sequence, where each term is the sum of the two previous terms. But it's not quite. You start with two ones, and then to get the nth term, you go back from where you are by the previous term, number of steps, plus the previous two steps back towards the beginning, and you add them up. And it's a sequence that begins very modestly, it grows, but if it should ever happen that the nth term was bigger than n, it would die, by definition. The requirement is that the nth term be less than n, less than or equal to n. And we don't know. It doesn't seem likely. Many people some people have studied this. But I thought, since we had such a strong group of sequence experts, we could settle this in the next 2 days. So here's how it looks. This is 200, the first 200 terms, and it goes 200 terms, we're up to about 100. It's growing at around a rate of 1/2. Not quite linear. There are fuzzy stretches, or sausages, which expand a bit away from n over 2, but not by much. This is an exaggerated plot of the difference between the nth q over n minus 1/2. And you can see it never gets too big. This is in the first 500,000 terms. The vertical scale up here, this is 0.06. So it's a long way from it. It's small in comparison. So the conjecture seems pretty clear. This is a plot that Douglas Hofstadter gave me that shows the first 100 million terms. And you can see again, it never gets very far from n over 2. Roman Pierce worked out that the sequence exists for 10 to the 10th terms. So it doesn't die for the first 10 to the 10th terms. But beyond that, it's not known. It doesn't seem like. You could probably compute a few more terms in a few minutes.
Might not help.
So that's one unsolved problem that I think is very interesting. Another unsolved problem is a much newer sequence, which was sent in by Jan Siemens van Eck from Utrecht. And this is a really nice sequence, and it's new. Sequence 181391. And it begins, here's how this is defined. It begins with 0. The first term is 0. And that's arbitrary, but that's how we begin, 0. Now, the rule is, if you see a number you've never seen before, the next term is 0. So we've never seen a 0 before, so the next term is 0. On the other hand, now we have seen a 0 before. We saw a 0 one step back, so the next term is 1. Right? Now we've never seen a 1 before, so the next term is 0. We have seen a 0 before. We saw a 0 2 steps back, so the next term is 2. So it's how far back you go to see the previous occurrence of that term. So we've never seen a 2 before, so we get a 0. And now we saw a 0 2 steps back, so we get a 2. We saw a 2 2 steps back, so we get another 2. We saw a 2 1 step back, so we get a 1. But now to see the previous 1, we have to go back 6 steps, so we get a 6. And then we get a 0, because we've never seen a 6 before. So that's the rule. Very simple. Lovely rule. This is what it looks like. This is the first 200 terms. This is the first 10 to the 5th terms. a log plot, and the upper envelope is essentially log n. And so let me actually prove something. Van Eck himself proved that there are infinitely many zeros in this sequence. You see, there are infinitely many new numbers that appear occasionally. The sequence is not bounded. You keep seeing new numbers all the time. And the proof is very nice. You say, well, suppose there are only finitely many zeros. So it's bounded. There's an upper limit. You never see, say, the numbers bigger than n, capital M. So let m be the maximum term. That means you never have to go back more than m steps in order to get the next term. So that a block of m steps determines the sequence. So there are only finitely many blocks of length m with numbers between 0 and m. But there are only m to the m blocks of length m. So a block has to repeat. So the sequence becomes periodic. And the period obviously doesn't contain any zeros, or else you would see infinitely many new things. So we know if it's bounded, then it's periodic, and the period contains no zeros. Well, all right, so let's look at the period. Let's look at the first occurrence of the period. Suppose the period starts at the rth term and ends at the suppose it has length p, it ends at term r plus p minus 1, and then it repeats. And suppose the period, the first term of the period is x, and the last term is z. So we say, all right, let's look at the second block. It begins with x again, and it ends with z. Let's look at the first occurrence of z in this block. It might be at the end, but it might be earlier. Let's say it's there. And let q be the next term. Then we go back to this block and look for this z, which is here, because this is the same block, just shifted. And look at this q. This q, because of the rule, says that z appeared q steps back, just as it did here. We went from z to z in q steps. Here we go from z to z in q steps. But that means that we have the same period going not from here to here, but from here to here. So we can move the period one step towards the beginning. So that wasn't, so we can repeat that argument and go all the way back to the beginning. Or we could have just said that's a contradiction, because we had assumed that we were looking at the first occurrence of this block. Or we can say that will enable us to go all the way back to the beginning of the sequence, that the sequence began with 0, and there are no zeros in the period. Either way, we get a contradiction. So this sequence is unbounded. And what seems to be the case is that the lim sup, every so often the nth, you get a term which is about n, which means you really have to go back almost all the way to the beginning, occasionally. And it looks like the gaps between the zeros are about log to the base 10 of n. It's just an empirical observation. And it looks like every number eventually appears. And we don't know anything about this other than Van Eck's original theorem. Another related question is, can you find a cycle? Can you arrange numbers around a circle so they satisfy the Van Eck rule? So, for instance, could we have a circle of numbers? Suppose we had 1, 6, 2. The 6 would mean there was a 1 6 steps back. Say this was a 2, that would mean that this 2 was 2 steps back. Can you arrange numbers around a circle so they satisfy the Van Eck rule? It's a strange kind of block design, and I don't know. David Applegate checked, you can't do it at length up to 14. You can do, there are trivial examples. You can put 1s around the circle, obviously, that satisfies the rule. But there are non-trivial examples. I think it's a nice combinatorial question. And there are a number of other unsolved problems. We started a bit late, I feel. Another unsolved problem is Leroy Quet's prime-producing sequence. This is something else that might not exist. So here's a sequence of primes. We begin with 2, and the rule is, for the next term, we want another prime such that n divides, we want a new prime p such that p plus the previous term is divisible by n. So we start with 2, which is the 1th term. And the next term, we want, sorry, that's the 0th term. 1th term has the property that 2 plus 3 is divisible by 1. We're looking for the prime 3, p, which should have the property that p plus 2 is divisible by n, which is 1. And 3 works because 2 plus 3 is divisible by 1. The next prime, 5, works because 3 plus 5 is divisible by 2. 5 plus 7 is divisible by 4. 7 plus 11, 5 plus 7 is divisible by 3. 7 plus 13 is divisible by 4. But 7 plus 11 would not be. So you always take the smallest prime that you haven't used already, which satisfies this condition. And we don't know that this sequence exists. It could, the condition is we're looking for a prime p such that n divides a n minus 1 plus p. So that means p has to be in an arithmetic progression whose common difference is n. And that's fine. We know there are infinitely many primes in an arithmetic progression, provided that the shift here, the offset, is not divisible by the step size. So this would die if n ever divided n minus 1. And, well, it could happen. David Applegate checked 600 million terms exist. But again, we don't know. There are many other unsolved problems, which I want to mention some new problems. So, this was a question that Max came up with. How many ways are there to draw n lines in the plane? So you have a piece of paper and a ruler, and you draw lines. So if you've got one line, there's only one way to do it. If you've got 2 lines, this is the affine plane, not the projected plane. So with 2 lines, they can either be parallel or they can cross. So there are 2 ways. So the second term is 2. If there are 3 lines, they can be parallel. You can have an H shape. You can have a star. Or they can be in general position with no intersection, no 2 lines intersecting. No point lying on more than 2 lines. So there are 4 ways of arranging 3 lines. So we get 24. And I worked out the next term, 9, and the term after that, 47. And then I finally discovered that this was not really a new problem at all, which I expected. And there are 2 more terms that are known. So here's the beginning of the enumeration of 5 lines. And there are 6 ways to put, G means general position. So there are 6 ways to arrange 5 lines in general position, which look like this. And so this is a subsequence. If you have n lines in general position, how many ways can you arrange them? And so there are 6 ways. And this is a sequence that Jonathan Wild and collaborator Reeves studied in 2004, and they worked out the first 7 terms. It turns out that, as you might expect, this isn't a new problem, and Lucas Finchi in Zurich, in his PhD thesis, he was classifying matroids. And he came up with a problem which is very similar to this. I mean, he was working with matroids a different language, but when you translate it into the language of lines, his lines could be